So this video we're going to talk about differentials. And so up until now, whenever I've referred to dy dx as a derivative, I've just referred to it as just a notation taken all at once. Dy dx, same thing as y prime or f prime. But now what we're going to get into is exactly what dy and dx are separately when we think about that dy over dx type of notation. So before we get there, we're going to start off and say, all right, suppose I'm at some point of what eventually is going to be my point of tangency interest here at c f of c, and I'm talking about some sort of small change, which I kind of wrote out in words there. You can't draw them so small, otherwise you won't be able to see everything that's going to come, but just keep in mind this delta x represents a small change in x. So a very small change in x, and it's the actual change in x on the on the original function here. We get into the tangent line in the next graph. So what we have here is a small change in x on the actual function. And so what that does is this small change in x that we have on this function is going to then result in, when you have a small change in x, this delta y, the actual change in y, you'll get a, somewhat of a small change in y. So we're talking about very small changes here, and we're on the actual function. Now, what is the actual delta y going to be equal to? Well, it's simply the change in y on the function. So if you started at c and you went out a distance of delta x, you're now at the point f of c plus delta x. So this actual change in y is simply going to be subtracting the y's. So the second y that results after the change in x, so f of c plus delta x, minus the first y value, f of c. Okay, and that should look reasonable, right? So we would go all the way up to this total height right here, right? That would be too much. And then we subtract off the height up to here. So we subtract that off, and then what we're left with is the delta y that we're looking for. All right, so that's what we have to start. And let's actually write these things down below. So I have kind of a summary of some of the things that we're looking at here. And so this, again, delta x is the actual, and I'll even kind of put in parentheses here, it's this small change in x on the function. And then the delta y is the actual, and again, we're talking about small changes, and this one sort of forces, this small change in x forces this small change in y on the function. And probably even more importantly then, as a formula, that is going to tell you that your change in y is your f of c plus delta x, so where you are on the function after the change in x, and then where you are in the function at that point of tangency. Okay, now we want to look at dy and dx. So dy and dx are going to be changes, small changes on the tangent line. So I'm going to kind of fill this in as we get going. So dx is the change, again, talking about small changes, so I'll be consistent, so right there. It's this small change in x on the tangent line. So now we're talking about a change in x on the tangent line, and the dy is going to be the small change in y on the tangent line. So first key difference here is really that when you're talking about the delta x's and delta y's, these are the changes on the original functions. So these are changes on the original functions. When you get into the dx and dy, these are the changes on the tangent line. Now, something else that we want to note, right as we kind of get started, and on this picture here, we can see is that delta x and the dx are exactly the same. So delta x and dx are identical. Okay, so those two are equal. All right, so now looking back at the picture, see visually, look at the difference in between your delta y. So this is the actual change in y on the function. So it's the difference between here and here. So this is your dy, the actual change in y on the function. Whereas the dy, so that's the delta y, the dy is as we go out to this f of c plus delta x. But if we do it on the tangent line, then the actual change on the tangent line, the change in y on the tangent line, that is your dy. Okay, so what we don't yet know, we already have our representation for delta y. What we don't yet have representation for is the dy. And so that's what we're going to need. So this is what we still need, is the dy. And what we really need is this y coordinate right here. Okay, it's the y coordinates of the point on the tangent line. So that's what we need. Okay, so we need, let's call it asterisk for right now. We need that point. Well, how am I going to find that point? It's going to be the change in y on the tangent line. So first of all, I've taken the liberty to write out on the tangent line here, there's that linearization. It's the general form for the equation of a tangent line that we talked about in the last video. So now what we need to do is we need to sub into that. So that point is going to be subbing x is the c plus delta x into that linearization. So what we need here is we need L of, I need L of, and I am subbing in, I need a new color here. Let's sub in the C, the C plus delta x. So that's the point that we are subbing into our tangent line. So if I look at the form of the tangent line, the form of the tangent line says it is the slope f prime of c, and then times the quantity of, and this is where I sub in my x value. And in for x, I'm putting in c plus delta x. So that's my x value. And then it's minus, and then going back to just my linearization, minus c, and then plus the f of c. All right, well, here's what we should, of course, notice is that the c and the minus c are going to become 0. So what do I end up with here? I end up with this delta x times f prime of c plus f of c. So that is the y value. So this value right here, this is the y value that we get when we sub in c plus delta x into our tangent line. Okay, so with that, to find my dy is just my change in y's here on the tangent line. So I take the value that goes all the way up to here, that's the value that we just found. So that is our delta x times f prime of c plus f of c. So I know it looks ugly, but that's what it is. And then we subtract off the height going up to here. So then we're left with just this height in that dy that we're looking for. So now I'm subtracting off then the f of c. All right, so when I do that, of course, we can see that our f of c's are going to reduce. And so what we get is this, I'm just going to change the order of my multiplication here, f prime of c delta x, and the f of c's have become 0. So this is my dy. Well, that's the big takeaway here. That's kind of really what we were most after. So now what we know, and this is really the main point of where we were headed, is that the differential of y is this f prime of c delta x. But of course, delta x and dx are the exact same thing. And c was just kind of, because we would have so many x's floating around, I just let c be kind of that point of tangency interest. It's going to be true for any x. So how we're going to write this is going to be dy equals f prime of x dx. Okay, so that is simply, so that is what this is right here. That's where we get this from. Okay. So that is kind of the most important piece of this whole thing that we have to now be able to use and work with. So what our whole idea was in this whole thing getting started is that when you're dealing with small changes, so remember I've been saying this all along, the delta x or the dx, those are identical, those are small changes in x, then that gives us these small changes in y. And what we kind of just observe even on the picture up there is that the dy is going to be a good approximation. So this is going to be a good approximation for the actual change in y. So this really gets back to the whole linearization concept, that the tangent line is a good approximation for the actual function for values that are close. So that's why when we're talking about small changes, this dy, the change in y on the tangent line, is going to be a good approximation for the actual change in y, because the tangent line is a good approximation for the actual function if we are close to those values. Close to that point that we're talking, the point of tangency interest. So that's what we're going to come back next time, and we're going to look at some examples using this differential of y.